T, which is an integer rectifiable area minimizing current, so a generalized surface. And about this generalized oriented surface, the only thing you know is that is the countable union of subsets of C1 submanifolds, right? So they can be fit in a very bad way, and they can actually get with multiplicity. So you might consider twice a surface or 3 times a surface, 3 times a piece of a surface, and so on. Okay, so it is an integer rectifiable area minimizing current, and so supported in some Riemannian manifold sigma. And the boundary of this current, I know it's actually a smooth given submanifold of sigma. Okay, so in the notation of geometric measure theory, usually the fact that you have something smooth underlying your current. So first of all, usually currents are defined in duality with differential forms. So you think that on these scattered pieces of C1 submanifolds, you integrate and form. And now, if you have something which is a nice submanifold to start with, which would be somehow, you just use this funny notation to say that you think that you're integrating over this gamma somehow, some form. So this like would be the current naturally associated to your submanifold gamma. Okay, and this is the boundary in the sense of current, which means actually that Stokes' theorem holds in this context. Okay, so now T is area minimizing means that if you give me any other S which is inside this Riemannian submanifold and it's bounding the same gamma, then you actually know that the area of T, the total volume of T, is less or equal than the total volume of your competitor S. Okay, and for the definition that I've given, T is actually made by countable union of scattered pieces of C1 submanifolds counted with multiplicity. The total area is simply the sum of the areas of the various pieces, which you just compute with the classical formula. And if you are counting them with higher multiplicity, then you have to multiply the area by the multiplicity that you're given. So if you're looking at twice the surface, then the area, I mean, the area of the current is twice the usual area of the surface. Okay? And for the purpose of this talk, I'm actually assuming that gamma is a submanifold of sigma. And for people interested in details, well, maybe first of all, let me just set the notation that so let me set the notation that the dimension of the current T is equal to m. So the dimension of the boundary gamma is equal to m minus 1. And the dimension of sigma is equal to m plus n. So of course, n is going to be what we will often call the codimension of your minimizer T. Okay, and for the people interested in details, when I'm saying that sigma is a smooth Riemannian manifold and gamma is a smooth Riemannian manifold, what I actually understand is that both sigma and gamma are C3 alpha for some positive alpha. Okay, so in all the results that I'm going to tell you in this talk. Okay, very good. So what I'm interested in is the regularity of this object, which is an area minimizing thing. So for instance, as soon as I can tell you that there is a neighborhood in which your scattered pieces of C1 submanifolds actually they form a nice single C1 submanifold, which is a graph, I can write a system of partial differential equations for them, for the graph from the Euler-Lagrange equation for the minimizing property, and actually I get then the usual Schauder estimates and I get smoothness. So in particular, if I am graphical in a certain portion, then sigma, then T will inherit the regularity that sigma has if I'm looking at the point in the interior. And if I am smooth in a neighborhood of a boundary point, in the sense that I am a C1 submanifold with boundary gamma, okay, then I will inherit the regularity of sigma and gamma. I mean, the minimum of the regularity between the two at that boundary point. So then I will be somehow C3 alpha. Okay? So the basic thing I'm interested in, therefore, is what I call regular points. So let me give you the following definition. So a point P is regular if, well, it's an interior point, so P does not belong to gamma, and then there exists U neighborhood of P such that, so now I have to restrict my current T to your neighborhood U. Of course, if I actually know the scattered pieces of C1 submanifolds which are underlying the current, I can just take their intersection with U. But if I'm thinking of the current T as acting on forms, I can just restrict the action of T on forms which are compactly supported in U. And in geometric measure theory, you then use the following funny notation for the restriction. Okay? So then what you want is that T restricted on U is going to be some multiple, some constant multiple of a C1 submanifold, say, I don't know, lambda. Okay? Where lambda inside U is a C1 m-dimensional submanifold. Okay, so that's an interior regular point. Let me just call over here interior. And now let me consider a boundary regular point. So now there are going to be two types actually of boundary regular points. And I mean the first one, which is the easiest to discuss, so let me call it this boundary regular point, the one-sided situation. Okay. So the one-sided situation is the following. So P now belongs to gamma, and there exists a U neighborhood of P such that blah, blah, blah. And up to here, T restricted to U is going to be now one single guy with multiplicity lambda. And now this time, lambda inside U is a C1 submanifold, but with boundary. So of course, I'm just considering the boundary of lambda inside U. So this has to be equal to gamma. Okay, and this is the boundary in the usual differential topological sense. Oh, I should also mention, so we are talking about integer rectifiable currents. So when I'm talking about C1 submanifolds, I always assume there is an orientation. So they're always oriented. Okay, I'm not going to repeat this. Okay, that's one situation, but it's not the only possible situation where you actually have a boundary regular point. So let me first give you a definition, and then let me motivate the definition. So here I will have what I call two-sided boundary regular points. Okay, I mean, so this is a P in gamma that exists a neighbor U, and then up to here everything is nice. But then I'm just telling you that T restricted to U is actually going to be two things. So Q times, and then I have some lambda plus, and then I have Q minus 1 times some lambda minus. Now, lambda plus and lambda minus are something like this. So somehow here there's your boundary gamma, and I'm imagining I have a lambda minus, which is on this side, and the lambda plus, which is on this other side. So what actually happens is that both lambda plus and lambda minus are C1 submanifold, but the boundary of lambda plus is equal to gamma, and this is actually equal to minus the boundary of lambda minus. Okay, so lambda minus comes somehow, picks this boundary with multiplicity Q minus 1, but negative. The other side picks it with multiplicity Q, but positive. And then, of course, when you're summing them in the sense of currents, so when you're integrating forms, the two things cancel, and you actually land with a boundary gamma, okay, as you want it. Now, it's not too difficult to see that if you have something like that, actually, the two tangents, they have to match. I mean, just by a simple variational argument, it's not possible that lambda plus comes somehow this way and lambda minus comes in this way, because then you could take q minus 1 copy of lambda plus and q minus 1 copies of lambda minus and sort of pull them in this direction to actually shorten the area, okay? While one single copy of lambda plus still remains fixed to actually take the boundary data, okay? So once you know this, you actually know that lambda minus union lambda plus, together they form a single C1 submanifold without boundary, which is in fact respecting the Euler-Lagrange equation for area minimizing currents. So in fact, it's as smooth as the ambient manifold is allowing you to be smooth, okay? So in this two-sided situation, lambda plus union lambda minus actually gives you some lambda, which is a C1 submanifold without boundary in U. Okay, this two-sided situation can actually happen. So for instance, assume I'm giving you, yep.
Do you get some regularity of the boundary curve then? You know,
yes and no. So what you get is this funny property. For instance, if you were in the Euclidean space, you would know that lambda is a Riemannian manifold, is an analytic submanifold, real analytic submanifold. So then you get the property that, for instance, your curve is lying inside a real analytic submanifold. It could still be a C1 curve, right? So because it's inside your real analytic submanifold, but somehow in the horizontal directions, it goes this way. Now, of course, it's still telling you some very strong information of your curve. So your typical, I don't know, CK or C infinity curve is not inside any Riemannian, any real analytic submanifold. So this should tell you that this two-sided situation, it might happen, but it's extremely unlikely that it happens. So if you give me a generic boundary data, I'm not going to have two-sided regular boundary points, okay? So this is going to be actually part of some funny remark later on. Okay, so back to what did I want to say now? Oh yeah, so this two-sided situation actually might happen. So say that I give you two circles which are oriented in the same way, right? So this is your gamma, and they are lying on two parallel planes. Okay, so then the minimizer is made by two copies of two disks with multiplicity 1. That's very easy to check. And now if you're sliding the first boundary circle towards the second, so if you're sliding the first plane towards the bottom plane, at a certain point when they collapse, actually the minimizer is going to be two copies of an inner plane and one copy of the outer corona. And so a point over here is exactly a point like the one I described up there. It's a regular point, but it's going to have one side which is counted with multiplicity 2, the inner side, and the outer side which is counted with multiplicity 1. Of course, it's absolutely important that you're considering the oriented plateau problem, and that the orientation of the two circles are really in this sense. Because, for instance, if I flip the orientation over here, right? Well, then when I get the two circles very close, the two disks are not anymore actually the minimizer, because it's much better to join the two circles in this way. Okay? But if you're joining the two circles in this way, then of course the two boundaries they must have opposite orientation. Okay? And of course, in this case, when you just collapse, you just find a corona with a hole inside. Okay? And all points are regular boundary points of the type one-sided. Okay, so now, regularity. What is known? So there is a huge difference between codimension 1 and codimension higher than 1. So codimension n equal 1. Okay, so then it's something that we know since the 70s that interior singular points, let me actually denote them by this. So by definition, interior singular points form a relatively closed set in sigma minus the boundary gamma. So this object has dimension at most m minus 7. Okay, so it has very small dimension. So this has been proved by a series of people. So the first regularity theorem is, in this context, is actually due to De Giorgi, and then there were some subsequent works by Almgren, Fleming, and then all the way to Simons and to Federer to actually get the dimension bound over here. And then actually there are further work by Leon Simon and Naber Valtorta, in which you also show better properties of your singular set. For instance, that the singular set is in fact rectifiable, not only that it has dimension m-7. Okay. Now, the boundary singular points, which I'm going to actually denote by this singular points at the boundary, is actually empty. So being at the boundary is much better than being in the interior in the codimension 1 situation. And this is a beautiful paper by Hard and Simon in the 80s. I think it's really like 1980, or if it's not 1980, it's 1979, something like that. OK. So now, what is actually known about the higher codimension? So codimension n equal 2. OK, so there is a famous work by Almgren, which is called Big Regularity Papers. So this appeared at the beginning of the 80s in the form of a very long preprint. And this is actually showing you that the interior singularities have codimension 2.
You mean codimension greater than or equal to?
Sorry. Yeah, sorry. They have dimension. OK, so they have dimension 2. So sorry. Sorry, has dimension at most m-2. And codimension at least 2. Yes, sorry.
Line above there, you mean n greater than or equal to?
Oh, yeah. Thanks. Otherwise. Yeah, absolutely. And Chang in 1988 so he actually proved that in the case of m equal 2, so in the first case where actually singularity might occur, the sets of singular points is discrete. So interior singularities are isolated. OK, so in fact, so Chang's proof is correct modulo one annoying thing, that is that you have to read whole the book of Almgren and then construct a certain object which is called branching center manifold. OK, so it's only sketched over here. And at the time he was actually writing the paper, it required reading this manuscript up to, say, page 1500. So it's, I mean, that portion is now done by myself, Emanuele Spadaro, and Lucas Polaor. And once you get actually that portion, you can get the paper of Chang, I mean, the portion of the proof which is written by Chang working. And this is actually based on some work by myself and Emanuele Spadaro, in which we have recasted Almgren's proof in a much simpler way. OK. So far, so good. Now, both. OK, so let me then say, so this is the interior singularities. So now, what about the boundary singularities? Well, up to now, the disturbing thing is that, so no information on the boundary singularities, except for some special cases. So no information on boundary singularity means in the general situation which I've told you, so somehow you're considering gamma in some Riemannian manifold sigma. As far as it was known up to now, actually this singular set could be the whole boundary. So the set of regular points could be empty. OK? So I will discuss this a little bit more in a couple of seconds, but just let me tell you two things. Well, all the results which are written on the blackboard are to a certain extent optimal, meaning, of course, there are singularities in the interior of codimension 7, is the famous Simon's cone. In the codimension 1, I mean, in the case of minimizing hypersurfaces, or you might call them minimizing hypercurrents, although I've never seen that in the literature. Of course, the fact that the singular set at the boundary is empty is optimal. Well, it's obvious. The appearance of singularities at codimension 2 in the higher codimension case is also optimal. And in here, although, of course, this is obviously very suboptimal, there are examples where there are boundary singularities at the boundary already when you have a curve in R4. Okay? So an important remark is, so boundary singularities, so this one is in general non-empty. Yeah, now I'm coming actually, so this is coming later in the talk. So we have more severe examples. In particular, we know that Chang's theorem cannot hold at the boundary if the curve is only C infinity. If it's real analytic, maybe still. OK, now before I go on, let me tell you that the main topic of the talk is actually a theorem which has a quite complicated proof and which is joined with Guido De Filippis, Jonas Hirsch, and Annalisa Massacesi. And it's actually telling you that the singular set at the boundary is meager, or if you want, the set of regular points, which is actually relatively open, is dense. OK, so what was known actually before this work? So I told you actually it's not like that nothing was known. But pretty much everything that was known went back to the PhD thesis of Bill Allard in 1979. So this PhD thesis actually was never published because, well, it was a beautiful result. I imagine the fact that it was superseded by his boundary regularity paper for stationary varifolds, which actually has the results of the PhD thesis as a corollary. Anyway, the PhD thesis of Bill at the time gave you the following information. So if you are in a Riemannian, I mean, if your sigma is the whole Euclidean space, and you know that your boundary gamma is lying on the boundary of a uniformly convex set, OK, then you know that your minimizer is actually fully regular at the boundary, so that the boundary singular points don't exist. OK, so now, although it looks like a global result, in fact, the argument of Allard is essentially local in the following sense. Well, there is one global information that you get, which is your minimizer T by a simple convexity argument has actually to lie inside U. And even slightly better. So the uniform convexity of the boundary of U is used in such a way to say that if you take the convex hull of gamma, right, the convex hull of gamma at every point P on the boundary is actually sandwiched between two planes which are meeting your boundary with a wedge, so at some angle. Okay? So that's where you're using that the thing is uniformly convex. So that is telling you, for instance, one very important piece of information, that not only once you conclude I mean, not only you will conclude that the boundary singular set is empty, but also that there is no possibility that this two-sided situation occurs. So you're always in this one-sided situation, okay? And that makes the big difference. I mean, in a sense, the fact that you have this global argument which is able to rule out the the two-sided situation is what makes this proof of regularity possible, okay? So the assumption excludes, so two-sided boundary points are excluded. And okay, so you actually don't need to have, I mean, if for some reason you know that you have a boundary point and you have a convex barrier which is kind of forbidding you to be on the other side, uniformly convex barrier, then the argument is actually local and you can prove local regularity, okay, at that point. So the global condition is only needed to ensure this kind of one-sided situation, okay? And in fact, the argument was the argument was localized in a paper by Hart in the 70s. So the whole mess of proving anything like this is simply due to the fact that there might be these two-sided singular points. And in particular, if I am in a global situation like being in a Riemannian manifold, which is closed, where I don't have a foliation by convex surfaces, so I don't have anything which is kind of giving me at least one point where I'm sure I'm lying on one side, then I don't know of any boundary regular point by Allard's theorem. I cannot apply it anywhere, okay? And in some special situation, for instance, when I am in the Euclidean space, I can take simply the smallest ball, which is containing my boundary gamma. It will have one touching point, and Allard's theory in hard version will actually guarantee that I'm regular at that particular point. Okay, so if I have some global situation, then I can actually ensure at least the existence of some boundary regular point. Of course, coming to Felix's question, the funny fact is that what is creating the nightmare is this two-sided situation, which a posteriori, it's an extremely unlikely event. So if you give me a generic curve, gamma, then a posteriori, once I've proved actually, for instance, this theorem over there, I can tell you that this two-sided situation never occurs. Or if it occurs, just perturb actually the boundary a little bit, and it will not occur. Okay? So I'm not going to tell you exactly what is the question of Almgren, but he poses this question. I mean, he essentially poses this question at the end of the big regularity paper. So the question is, if you are, it's not exactly phrased in this way, but let us phrase it in this way. If you give me a connected boundary gamma inside any sigma, can you actually show that there is at least one boundary regular point which is one-sided? Okay, so the example which I've given you needs a disconnected boundary. And then if you actually have this property, you can show that the minimizer is a connected submanifold except for the singularities. And now this theorem actually answers to that question. So once you actually know that there are boundary regular points, if you know a priori that your gamma is connected, then you can actually show that the boundary regular points that we found are one-sided. So it takes like a couple of 100 pages to prove that there are boundary regular points. Then it takes a couple of lines to tell you that the reason why you had a 200 pages proof, if, for instance, gamma is connected, is just not there, right? So you actually, for these 200 pages, just wanted to handle the case of two-sided boundary regular points. But then you discover at the end that you actually didn't need to do it. So I don't know. I mean, if one found an easier way, at least for connected gammas, to tell me that the points are all one-sided in some sense, then I would have actually regularity from Allard. But I don't know that. And the theory is completely local. So of course, in some cases, actually, there will be two-sided boundary regular points, and I'm able to capture them with that theory over there. OK, so now, yeah, I guess I have to do this. Yep. OK, so now let me tell you one reason why, and this is actually a more difficult theorem than the interior regularity theory. Well, okay, of course, one thing that you would discover if you just look at the proof is that the interior regularity theory is essentially all used. So it's on top of the interior regularity theory. Okay, but let me also give you a specific reason. So there is the following example that we have in the paper, and I think we were very lucky that this example we found after proving the theorem. Because if we had found this example before proving the theorem, I'm not even sure we would have tried to prove the theorem. So let me explain you why. So this example, which luckily came much after, is a C infinity curve, gamma, in R4, which has a countably many singular points, I mean, whose minimizer has countably many singular points at the boundary, clustering towards, of course, some point at the boundary. So C infinity curve, gamma in R4, such that the unique minimizer which bounds it, I mean, it has a unique minimizer bounding it, the unique minimizing integral rectifiable current T bounding it has countably many boundary singular points. Of course, this is a C infinity closed curve. So if there are infinitely many boundary singular points, they have to converge somewhere. Well, in our specific example, they are converging towards the origin. But okay, and this tells you that the theorem of Chang, that is that the singularities are isolated at the boundary, cannot be correct. Because this example has, in the origin, a boundary singularity which is not isolated. Okay, and now, why I'm saying that this would have been discouraging before proving the theorem? Because, so this is, I mean, this theorem mimics in some sense, to a certain extent, the interior boundary regularity theorem of Almgren. But when you actually look at this specific example, if you try to reproduce that specific example, I mean, Chang is more complicated, but if you try to reproduce that specific example in the interior, it's exactly the starting point of his boundary regularity theory, that there cannot be such an example of points of singular points which are clustering towards an interior singular point in the interior. So it looks like that, you know, what you would try to do, which is translating the interior regularity theory to the boundary, it hits, I mean, you would imagine if I'm able to do that, then I should be able actually to exclude this example over here, which you're not able to, okay, because it exists. So before I actually go on, let me tell you that there is a conjecture by White. The conjecture was done before we had the example. So, but there is a conjecture by White which says that if gamma is real analytic, then the set of singular points is finite, even at the boundary. And actually, the union of the two, right? So because one thing that Chang is not excluding, and one thing that we can actually not exclude either because we can modify the example so that that is not correct, is that there is a sequence of interior singular points which are clustering towards the boundary. Okay. So what happens when gamma is real analytic? Well, in the case of a C infinity curve, we actually get a boundary branch point, which is 0, which is a cluster of, I mean, which is the cluster point of a sequence of singular points at the boundary. But the singular points at the boundary, they more look like crossing of planes. Okay? So actually, there's a theorem by Brian which says that if gamma is real analytic, and you know this conjecture, then the boundary singular points cannot be branching. Okay, so that example cannot be, of course, made in the case of a real analytic. And it's not unconceivable, well, in fact, I hope to, or we hope to, that our, that the theory that we have developed to actually tackle this theorem would give us this conjecture by White. So it's maybe not such a long shot, but we don't yet know how to prove it. OK, so now what is the upshot of the proof then? So why, although it seems actually from the example that we shouldn't be able to prove the theorem over there, we are nonetheless able to prove it. Well, of course, the devil is in the details, but at least I can give you some heuristics for that. Tangent cone at the boundary at that 0 is just 2 copies of half of a disk on one side and 1 copy of the other half of the disk on the other side. The typical thing that you would find actually at the branching point. And I mean, if it were not for the kind of self-intersecting of the current, locally the guy looks like a branching singularity, but the branching singularity has a C infinity order of contact with 0. That's the point. So for instance, the usual argument with the frequency function, which would tell you that, you know, the branching singularity has to detach a little bit from the cone, is not working. Which is the reason why you would believe, then you shouldn't be able to prove that theorem, right? So because that is kind of the deus ex machina of Almgren's proof. So, OK. Right. So first of all, what is the enemy in this case? OK, so of course, you need to have an enemy to understand why you can prove something. So the interior singularities of the following are, I mean, the typical example of interior singularities are of the following form. And somehow, if you want to prove that this is locally an area minimizing a current, you need the theorem by Federer and Wittinger. Oh, by the way, wait a second. Before I forget, that example is inspired by a paper of Gulliver. Where there is a similar example with a stationary surface, which is related to the Douglas-Rado approach to the Plateau problem. Okay. Okay, so this example, which you know it's a minimizer by a theorem of Federer, which is computation of Wittinger, is if you take something like the branching of an holomorphic curve in C2, which you regard as R4. So this is a singularity. Okay, so this is the typical singularity that you encounter, and after you actually prove Chang's theorem, it also has, I mean, the whole theory also has an effect that, quote unquote, the singularities that you encounter in codimension 2, they are all of this type. So in particular, for two-dimensional surfaces, the singularity are all of this type, or of the type of crossing planes, which are actually easier. Okay, so but the complicated singularities, they are all of this type, modulo diffeomorphisms and sort of extra complications. So what you would like to exclude, for instance, if you want to prove Chang's theorem, is that a sequence of guys of this type is actually clustering in the interior. Okay, so for an holomorphic curve, you would immediately know that this is not possible, because it would be as if you had an holomorphic function which has a sequence of zeros which is accumulating in the interior, and that's not possible. Okay, so the upshot of Almgren's proof in one line is that, so there is a way, complicated, but there is a way of proving a unique continuation type result for area minimizing surfaces. The unique continuation type result is, so H, say, from some omega in C into C holomorphic, then zeros are isolated. And now here, of course, is the bad news. If you think of it in this following way, I mean, in this way, of course, at the boundary, there's nothing like that. I mean, if I give you on the upper half complex plane an holomorphic function which has a C infinity boundary data, I can, of course, cook up a sequence of zeros which are accumulating towards the boundary. There's nothing wrong with that. Okay? Of course, if you're real analytic at your real axis, okay, then you can continue your holomorphic function further on, and there's no way you have actually a sequence of zeros accumulating towards the boundary. And that could be a rough explanation of why you could expect this conjecture of white to be correct. And it's a rough explanation of why actually you find this example. But it's a very rough explanation because the example is rather subtle. Huh? So it's, I mean, but somehow ultimately you have to cook up the correct holomorphic functions which have zeros which are converging towards the boundary with a C infinity boundary data, and you have to sort of arrange it in a very smart way to actually get that counterexample over there. Okay, but it's by no means obvious. Okay, so now what happens when you actually have the situation of this theorem? So what happens is the following, but of course this requires, I mean, this requires half of the proof essentially. So it's a very complicated proof, but this is what happens if you assume that your singular points have non-empty interior, rather than being a situation in which you want to exclude a sequence of zeros of an holomorphic function accumulating towards a boundary, you have the extra information that your holomorphic function is actually 0 at your boundary. In particular, if you were in the upper half plane, of course, you would be holomorphic on the real line. Okay? So it's a lot of work, but somehow the assumption that there are no regular points on some interval, for instance, of your curve, or in a more complicated way in higher codimension, tells you that there's a way to reduce it to unique continuation of holomorphic function when you actually know that your boundary data is equal to 0. Okay? So now that actually does not at all give the proof yet. I mean, there's another 100 pages of work to do, but so at least let me give you the insight on these other, I mean, like the most important computation of these other, say, 100 pages in the proof. And so this will be my last 10 minutes, hopefully, and then it's the end of the talk. Okay, so I'm actually looking at the following very interesting toy problem. And now, so I've given this talk actually plenty of times, and every time I've actually proposed the toy problem, I got like 10 proposals for solutions of the toy problem. Because the toy problem can be solved by a reflection principle, Schauder estimates, whatever. I mean, it's a PDE problem, and there are like, I don't know, 10 different approaches to it. Now, the point of the toy problem is that I need something which is super robust and super elementary for the toy problem, because my actual problem has very, very little to do with this toy problem. It's really like a vague analog. So it's not like I can take the classical PDE proof and transform it into the proof of the theorem, because I don't have any PDE to start with in the situation where I want to prove the theorem. Nonetheless, I think it's a cute toy problem. So I mean, even though I think it's misleading, I mean, I learned after that it's misleading. Nonetheless, let me give it to you. So here's the toy problem. I have some boundary gamma. Now forget about currents. I mean, this is just, you know, all functions and nice sets in Rn. So here you have some boundary gamma, say in some Rm. And gamma, of course, is a boundary of an open set. So gamma is smooth. And has codimension 1. Right. So now I have a function on this side. It solves Laplacian of u equal to 0, and it solves u on the boundary equal to 0. Okay? I insist, on the other hand, that I don't know that this gamma is regular. I mean, this gamma, for instance, might be just C2. Well, let's say it has a certain amount of regularity, but it's not real analytic in particular. Now, if this were a straight line, I could actually use the Schwarz reflection principle, right, and construct an harmonic function which is going after. And if this were a real analytic boundary, I could use Cauchy-Kowalewski and actually sort of prolong my harmonic function later on. But this boundary is an honest, for instance, C2, C3 boundary, and I cannot go with an harmonic function on the other side. Of course, I could use some of the classical techniques to deal with boundary regularity problems. I can try to straighten the boundary. I can try somehow a reflection trick, and for instance, write down a PDE, which now has variable coefficients, and whose variable coefficients are not so nice across the boundary, but they're nice enough to actually infer some conclusions. That I can do, and together with this, I can do another 10 possible approaches, and none of them is actually going to be useful anyway to prove that theorem that I know of, right? That I know of. Of course, it might perfectly be that if you're good enough, you can smuggle some of the more classical PDE techniques rather than going through this nightmare. Anyway, so how would you prove the following theorem? So the theorem would be the following. Sorry? I'm going to tell you the theorem. The theorem is the toy problem somehow. So the toy problem is prove this theorem in the least painful way. Of course, like, okay, since I'm setting the rules, so give me a proof which will make me happy. So it's a kind of, I understand it's a bit unfair, but I mean you will see what kind of proof I'm aiming at. Okay, so 0 is actually in gamma, and I assume that 0 is an infinite order of contact of the function with the function identically equal to 0. Okay, so now this is something that you can prove in several ways, but I mean, if you have the same problem in the interior, sort of the key analytic idea of Almgren's big regularity paper is the following. So if 0 were in the interior, assuming you have a non-trivial function which has, I mean, assuming u is a non-trivial harmonic function, of course, it's like in that situation, right? So Laplacian of u is equal to 0, u at the boundary of gamma is equal to 0. So if 0 were in the interior and u were non-trivial, okay, then Almgren's discovery, which I actually learned my final year. So I always thought actually Almgren was the first one to discover this property, the monotonicity of the so-called frequency function. But when lecturing actually in the Hebrew University of Jerusalem, Dan Mangubi told me that Agmon had this computation, if not much before, but a couple of years before. So it's in a paper of Agmon a couple of years before, but it's not used by Agmon in the same way as it's used by Almgren. So, but the monotonicity would be there. So the following quantity is monotone. Being monotone, it has a limit. And somehow, appropriate rescaling of your function u, when you're zooming into your point 0, are converging to a function which is I0 homogeneous. So that's a fancy way to tell you that this I0 is the degree of the first non-trivial harmonic polynomial in the Taylor expansion of your function u at the point 0. Okay? But I mean, the beauty of this is that you don't need to have any regularity, you don't need to know any real analyticity to actually get this number and to get the conclusion that that 0 cannot be a point where the L2 norm decays as fast as you want, right? So because this I0, which it's a huge number maybe, but it exists because by monotonicity, so the monotonicity that I didn't write over here is that I prime of r is bigger or equal than 0, and so the monotonicity tells you that if you compute this on the ball of radius 1, it gives you a bound for this number I0, okay? So now, what is the upshot if you are actually at the boundary? Well, if you are at the boundary and you try to mimic the proof of the monotonicity of this object, you actually run immediately into a lot of problems. But there is a Q theorem that you can prove, and it's a very simple thing to prove. And this is what we prove in this paper together with Guido, Jonas, and Annalisa. And now I was arrogant enough not to actually write down any notes. I'm not sure I'm going to get the formulas precise. But anyway, so if you take phi, some test function, which I just need to be bigger or equal than 0, and I need phi prime to be less or equal than 0. So the type of phi I'm looking at is something like this. Okay? And if you have the kind of distance function from the point 0, which has the following property, so it is like modulus of x plus higher order corrections okay, up to 2 derivatives. And of course, if I'm differentiating over here, then here I get minus j. Okay, and this I need for j equals 0, 1, and 2. So under all these conditions, if in addition I know that the gradient of d is parallel to my surface gamma, so here I have that the gradient of d is kind of like this, and this is telling you why, for instance, I cannot use d equal to modulus of x, but so there will be a little lemma which tells you if gamma is regular enough, such a d as over there exists, then the cute thing is that you can write a perturbation of the frequency function which looks like this. So you can write I phi d of r. So now, hopefully I remember this correctly. So here I have the integral of phi of d of x divided by r, and here I have modulus of du squared. Okay, and now below, and here's where the thing gets more complicated, and I'm hoping I'm getting the correct thing. So here you need the integral of phi prime, probably there's a minus over here, of d of x divided by r. And then I think you have modulus of u squared of x, it's divided by d of x. And then what I don't remember, there is a modulus of gradient of d squared, but I don't remember if it's in the denominator or not. Okay, so let me put it over here. But this might be wrong. Okay, then this quantity sort of is a surrogate for the frequency function. It captures modulo constants, which depends on this function phi the I0 as before, but you cannot exactly prove that this guy is monotone. This guy is monotone up to an error. And the error is something like e to some constant, and then I think you need this r to the alpha I of r. So this one is monotone. Okay, and so this is the main reason why we can actually then carry on the other half of the proof. Well, not completely, because somewhat this computation is maybe even used somewhere hidden in the first half of the proof, where I want this property that having all boundary irregular points gives you kind of this touching condition at the boundary, right? But of course, what you notice immediately is that Almgren's frequency function, I mean, if I were in the interior, then this condition that the gradient of d has to be parallel to gamma would be completely empty, and you would prove exactly the same monotonicity, okay? The fact that the gradient of d is parallel to gamma is just used to make some integration by parts at the boundary in a certain sense. Of course, what you would notice is that if you were in the interior and you would pick d of x to be exactly modulus of x, and you would pick actually phi to be an extreme case of these tests, so to be just the indicator function of the interval 0, 1, which is just undergoing a jump, and then it's identically equal to 0, then of course this function would reduce exactly to the Almgren's frequency function. So this is just a two-parameter perturbation of the original one by Almgren. And okay, sorry, I actually intended to finish before. Sorry?
The integrals are over what?
The integral is all over the whole space because somehow, oh yeah, okay, I didn't tell you this function phi. I wanted it compactly supported, right? I mean, it's a cutoff function phi, right? So and then it's actually the rescaling with r, which is taking care of the fact that you're integrating on smaller and smaller balls. Yeah. Okay. That's all I wanted to tell you. I actually planned to finish before, but yeah, I'm still on time. Thank you.